So, hello Berlin. I'm really excited to be here in the droidcon 2024. And today I'm going to present my talk. It's called Jetpack Compose, Drawing Without Pain and Recomposition. In my session, I want to present some advices I've discovered myself, which can help reduce the amount of recomposition and, in some cases, memory allocations when using Jetpack Compose in certain situations. Minor spoiler, there will be some pain in this session too. So, a few words about me. My name is Vitalii Markus, and I'm an Android engineer at Floor and droidcon speaker. I have more than 7 years of experience, and I used to work in fintech, food tech, and right now I'm super enthusiastic about working in Floor, which I joined almost 2 years ago. As a part of the Health Monitor team, we are responsible for some features, which I'll describe a little bit further. About Flow application, so we began as a period and evaluation tracker application, but over time we started integrating new features that helps users daily. The app has more than 300 million installed. It's translated into 20 different languages, and it has 65 million monthly active users. So we started integrating Jetpack Compose a little over 2 years ago. For the first year, we mostly experimented with the small features, but in the second year, we began writing more and more features in Compose. Currently, 40% of all screens in our application are written using Jetpack Compose. And we are moving forwards to a Compose-first approach, meaning all new features are done exclusively with the Compose. And also, I'm very excited that we've implemented our design system using Jetpack Compose. So what we already done that is quite large and significant. We completely redesigned the main screen using Jetpack Compose. We created a symptom panel where a user can log their symptoms, note the mood, and track their life events. And we introduced a symptom checker. So the system checker is feature that is based on various user data collected automatically and manually from the chatbot dialog, provides a match of probability of one of the predefined conditions. For example, on this screenshot, we can see that the user has a significant match for the endometriosis. Okay, so today we are going to discuss the recomposition, what is very briefly and quickly, triggers of recompositions, how to optimize it, how different clients follow the same approach. I will also touch memory optimization a bit, and we will likely a conclusion at the end. So I want to say that this talk was inspired by Filip Novak and Andrei Shikov. I attach links to my presentation so you can see sessions later. Okay, let's start with the Jetpack Compose phases. As we all know, Jetpack Compose is a new declarative framework for displaying data on the UI. It consists of 3 phases: composition, layout, and drawing. During the composition phase, we determine what we want to display. In the layout, we specify where we want to display. And in the drawing, we actually draw it, or how we want to display it. And by the way, the layout phase itself consists of 2 sub-phases: measurement and placement. In the measurement phase, we calculate the size of our composable, and into the placement phase, we position them. Let's look at this code example. When we use modifier size, we specify the element size during the composition phase. The measure method and its rounding code are executed into measurement phase. The placement phase, in the placement phase, we position our placeable, which was calculated previously. And in the drawing phase, it's quite straightforward, and we will discuss a little bit later. So let's discuss what triggers recompositions. Generally, recomposition happens when state value change or the function input argument change. The state value can be changed from the UI, view models, or at any moment during any phase. We can even update data during the composition phase. Also, it's not recommended because it can cause an infinite loop. But Compose can also handle it. And when data is updated, we go through the composition and all other phases again. And this cycle could be called a recomposition. So if you check the article on androiddevelopers.com with the name Follow Best Practice, they recommend using 4 core principles. Remember to minimize expensive calculations, derive state off to limit recompositions, and using stable and mutable classes and lazy layout keys. To recompose, only change item into lazy list. These principles are just to remind you. I want to spend any time of this. Let's go to the first example with alpha. On this slide, we have a general button on the screen, and in the on-click action, we update the state. Based on this state, we animate the alpha from 1 to 0.5, and vice versa. Here we read this value, and let's check the recomposition count. Yeah, I think we all know that there is a lot of recomposition during the animation. But how we can avoid it? I think we also know that there is another modifier that is called graphics layer. It does the same thing, but without causing additional recomposition. Let's check it out. So as you can see, there is no recompositions at all. But why it's happening? Let's go to the documentation. This version is preferred for reading animated or frequently changing state. In this case, we just update the layer properties, which does not cause additional recomposition. And if you notice, we're in the graphic scope. So we read our states only into the drawing phase. Okay, let's try to create the custom extension alpha layer. And when we run the video, we can notice that the result will be exactly the same in the first case. This is happening because even though we change the alpha during the composition, we still read the state into we change the alpha during the drawing phase, but we still read the state into the composition phase. So does the phase where we read the state affect the recomposition count? And it looks like it is. But before going to the next topic, let's take a look on the different phases of the Jetpack Compose, how to understand how and where we can read compose states. Here on this slide, we're using modifier size. We read the width and height during the composition. So every time when we pass a value into a method, modifier, or any composable function as an input argument, we read the state into composition phase. On this slide, we are trying to create a custom height modifier. We read the state into layout modifier during measurement phase. Next, we create a new constraint, set the minimum and maximum height, measure, and finally, we place the element. And by the way, I want to highlight that the position of the size of the box are identical to the previous one. On this example, we read state into placement phase, and we apply it to a place function. So here we've created a kind of custom implementation of the modifier set. And in this last example, we are using draw with content modifier. With this modifier, we draw a line above the content. And inside this draw modifier, we read the state of the stroke width into the drawing phase and pass it to a drawLine function. So, why is it so important to understand on which phase we read a state? Basically, when a change in state triggers re-executing of one phase, the all next phases also will be re-executed. And on this slide, you can see the average time of each phase, and we can notice that the composition phase is the longest one. So if during the composition we read frequently changing state, the composition phase, and moreover, layout and drawing phase also will be re-executed. However, if you read the changing state only in the layout or drawing phase, the composition won't be triggered and will be skipped, saving time and improving performance. And this is exactly what we observed in our first example with changing the alpha for a button. So let's return to our best practices. We already have 4 well-known principles to improve our performance. And now, let's add a new one. Defer reads as long as possible. So what is it? Let's go to the example. Here we have a simple example. We have a foo1 function, which has a mutable state inside, and every 500 milliseconds, we increment the value. Then we pass this value to a foo2 function, and then to foo3, foo4, etc. At the end, foo5 function displays the state into a text. And as you can see, when the state is changed, all nested functions are recomposed, although foo2, foo3, and foo4 haven't changed anything. They just pass in a value to the next function. So what we can do, we can defer the reading. We can do it in 2 ways. The first one is pass the state directly and read it using its value property. Or the second one, for example, we can pass a lambda, what does the same thing. To be honest, there is no much difference. I think it depends only on your preferences. And when they run this code, we can see that the behavior remained the same, but the number of recomposition has significantly decreased. The function bar and bus 1, 2, 3, and 4 are not recomposed because we don't read the input argument in this function. We simplify, pass an argument further, so function does not subscribe to changes of input arguments, and the compiler optimizes the compositions. So we read the state only in bar 5 and bus 5 functions. That's why only this function and text functions are recomposed in our case. And this is an example of our 5th point, defer reads as long as possible. Okay, let's go further to the next example with the height, for example. So there is a basic example. Here we have a button, and when we click on it, we change the state from expanded to collapsed. Based on this state, we change the text and the height of the element. We read it into height modifier. There is no animation, and as you can see, each click changes the state and triggers only one recomposition. Now let's try to add animation. In this example, we just replaced if to the animate DPS state function. Nothing else has changed. However, we can see that during the height animation, a large number of recomposition occurred. Why does it happen? Because we read the state during the composition phase, and we want to avoid it. So let's try to achieve it in a different way. It requires a little bit more work, but we can create a custom height modifier that accepts not just DP, but for example, in our case, state of DP. And let's check how it affects recomposition. The amount of recomposition has decreased significantly. Let's try to understand what's happening under the hood. On the left, there is the source code of the original height modifier. And on the right, our custom solution. And as you can see, the main difference is that the library code uses DP, and our custom solution uses state of DP. Later, we try to create target constraint in our modifier. In the library code, we read all states, all DP properties, and our custom modifier, we read state via value property. And this is the whole difference. But the most important thing is knowing at which stage we read these target constraints. We read target constraints during the measurement phase, and measure scope confirms it. So this means that we move the read in our height from a composition phase to a measurement phase, thereby eliminating excessive recompositions. And by the way, we can achieve the same behavior with another modifier that accepts lambda. But let's try to do it without custom modifiers. There is a standard tools to have the same behavior. We can use layout modifier, and inside this block we can read the height value, create new constraint, set minimum and maximum height, and later place the element. If we run the animation, we see that there is no recompositions at all. So we again move reading our height from the composition phase to the measurement phase. Let's go to the next example with the background. This example is also very simple. We have 3 different colors, a shade of red, blue, and purple. When we click on the radio button, we change the state and start the color animation with the method animateColorState. Then we read this value in the background modifier. And again, we have a lot of recomposition in Layout Inspector, because we again read the state during the composition phase, and we want to improve it. The idea is to use the same approach that we already described with the height example. We can create a custom background modifier which accepts lambda instead of pure color. And in this case, the amount of recomposition significantly decreased. So how does it work? On the left part of the slide, there is the source code of the background modifier. And on the right, our custom one. As you can see, the main difference is that the library code uses color and brush, and our custom solution uses lambda for getting color and brush. And there is only the single difference between these 2 implementations. But again, the most important thing is knowing at which stage we draw a background. And in our case, it's a rectangle. We draw it during the drawing phase, and draw scope confirms it. On the right, we read color from a lambda with the invoke method into the drawing phase. And it means that we again moved reading our background color from the composition to the drawing phase, thereby eliminating excessive recompositions. And we can achieve the same result with another background modifier that accepts lambda, that accepts state. But again, let's try to do it without custom modifiers. There is standard tools. We can use modifier draw behind or any draw modifier. Inside this, we draw a rectangle, in our case, but in your case, it could be any shape, any color, or any brush. And in the video, we see that there is no recomposition at all. So we again move reading our state from the composition to drawing phase. Okay, let's return to our slide with the best practice, especially to the last point. I want to add to the last point, defer reads as long as possible and use some point, even changing phases, which means that we can defer reading to a different phase to improving our app's performance. Okay, let's see how this approach is used by Jetpack Compose and some libraries. There is a few examples. I think the most famous example is offset. In this example, the offset takes a value as a dp as an input argument. And when we click on the button, we start the animation, and it changes the offset from 0 to 100. And during the animation, we read the state into composition phase. That's why there is a huge number of recomposition into layout inspector. Yeah, let's show it again. However, we also can optimize it. We can use another version of offset modifier that takes lambda as an input argument. Inside it, we can convert dp to px, and all operation, including reading the state, will be executed into layout phase. And this is one of the several examples how we can avoid excessive recompositions. Let's go a little bit deeper to understand. On the left one, the left one is the modifier that takes dp and creates offset node inside. The right one takes lambda and creates offset px node inside. The first modifier and offset node uses dp, so we can say that it reads the state value at the creation time, which happens during the composition phase. Meanwhile, the second one take a lambda and call it only into placement or layout phase. This is how we move to reading our state from one phase to another. Let's go to the next example. In our application, we use Lottie, quite a lot of. And let's try to understand how it works. This slide showed the composable function for Lottie animation. It takes Lottie composition and progress value from 0 to 1. To call this composable function, we have to create Lottie composition with the required resources and animate it as a state. The state contained a progress value, which we pass to the next function. And let's run the video and see what's happening. Yeah, we can notice that a significant number of recomposition practically on every animation frame. But I found something interesting. The number of recomposition is limited. When the animation completes one iteration and starts a new one, there is no more recompositions at all. It seems like Compose caches them for optimization. Honestly, I haven't figured out this yet, so if anyone has an answer, yeah, I would love to hear it. And the implementation side is also very simple. The library creates a drawable, update the progress, and draw everything on the native canvas. So when everything is happening into drawing phase, into draw into canvas function. In the version 5.0, the developers decided to optimize library bit, and they released a new version of the API. Now the progress is passed as a lambda argument. What does it give us? Let's run the video. So right now we don't have recomposition on every animation frame. But why? Because right now we invoke function during the drawing phase into draw into canvas function. And here it's one of the examples how the developers move reading the progress value from the composition to the drawing phase. And so, like, quite obvious question, should you do it everywhere and every time? It's a really, really good question. But if we create super simple example, only with one button and click several times, we can notice that the button is recomposed up to 20 times per each click. This has happened because of the elevation. It's a composable function that returns state of DP and the value read during the composition phase. So in this case, I think I follow the common principle, please optimize only when it's necessary. Because in the pursuit of the optimization, I think you can make the code completely unreadable. Okay, Let's go to the next topic. It's regarding the memory. In our app, we have a custom implementation of component that is called Shimmer. It shows the loading progress for required components as on the video. The API's implementation is very simple. It wraps the content into a box and sets a custom modifier. So we are good developers and we want to implement it in optimize into the best way. So we want to implement the optimized version of this. So let's use drawing. We create a custom modifier and run the endless progress animation that changes value from 0 to 1. This value is represented the position of our stripe. Since we aim for a more optimized version, we'll use draw with cache modifier. Inside it, we create gradient brush and draw a rectangle over the content with the specified coordinates, sizes, and brush. For testing, I used purple and green colors for a gradient to make it more visible. And if we run the animation, we see what is shown on the screenshot. The green stripe moves, but the purple one doesn't. So something is wrong with our implementation. And let's try to fix it. The problem occurs because we only move in the rectangle, but we also have to move brush coordinates. And as a result, we have to recreate the brush on every frame when start X value changes. This essentially rolls back all benefits of using draw with cache modifier. And let's check the memory allocation for this example. If we open the profiler, we can notice that during the shimmer animation, the linear gradient from the compose was created 1,363 times, and the native Android linear gradient was created the same number of times. So it appears that we are creating a linear gradient object on every animation frame during our drawing phase. So we must optimize it. So the idea is to use method with appeared in the first API, and it's called canvas translate. It moves the canvas to the new coordinates and allows drawing the same elements and the new coordinates without changing any logic. With this method, with the translate method, we can now cache our brush and just call draw rect inside the translate block, where we move the canvas for static coordinates. This solution provides the correct behavior and saves memory. Let's check how it affects memory allocation. And as you can see on this slide, we create only one instance of the linear gradient into Compose. To be honest, I have no idea why we have 3 instances of the native Android linear gradient, but it's much less than it was before. So I'm quite satisfied with this solution. So for example, there is another way to implement a shimmer. We can use offset modifier with lambda. This modifier is executing during the layout phase, unlike the previous solution which was executed into the drawing phase. And as you remember from our previous slides, drawing phase takes less time. So we can say that the previous solution is still considered as more optimal. And let's go to the last example with the particles. So on this slide, we have 2 screenshots. There is the main screen of our application. The left one is an old design implemented with native Android views. And the right one is the new design, which is fully implemented with the Compose. So we have implemented a particle system in both frameworks, or we call it like the spoiler animation. So let me explain how we've implemented it and the challenges we faced during our implementation into Compose. Basically, the particle system is built on a single principle. Every X milliseconds, the coordinates of the particles are recalculated and all available particles are drawn with the new coordinates. So this is the source code of the particle system. It has a draw method, and inside it has it called the internal implementation. We pass the bounds of the area where the particles should be drawn, and the lambda arguments specify the emitter function responsible for a drawing. The function draw particles calls native canvas draw points, passing the float array of coordinates and the numbers of points to be drawn. If we want to implement the same functionality with the compose, we just need to write a new method that works with the draw scope instead of canvas. And fortunately, draw scope has a similar method, draw points, the same method, draw points, with the similar arguments as the canvas method. And in the same way, we create a method for a particle system. The single difference here is that instead of canvas and rect, we are using draw scope and compose size. This slide shows the implementation of the composable function. We create a particle system and state that is hold the current time. In the launch effect, we update the current time every 33 milliseconds to achieve 30 FPS animation. Then we call our draw method and pass the draw scope as a main parameter. So let's check how it affects memory allocation. Whoa! After analyzing the profiler, I noticed that more than 79,000 offsets were created during the animation. Why are these such huge numbers? Where do these values come from? We need to figure it out. Firstly, let's open the source code of the offset class. Offset, it's a mutable value or inline class with the x and y coordinates packed into a single primitive long type. So it means that, theoretically, there shouldn't be any memory issues, since the creation of the primitives occurs not in the heap. But there is one stuff that is called boxing. If we check the source code of the draw points function, we can notice that the points argument is the list of offset. That's why the extension method toPoints return list of offset, which is delegated to the draw points function. And as we know, any primitive or value classes, when they're used or pass to a method as a generic type, and list of t is definitely generic type, all primitives and value classes will be boxed. So for us, it means that on every animation frame, we create a new list with the all new offsets and pass it to the draw points method. That's why we have a lot of allocations of the offset object. So to optimize the performance, it would be preferable to use the same float array which we used for a canvas or native canvas implementation. Fortunately, there is a solution. You can access to the compose canvas from draw context. The compose canvas has a method called draw raw points, which is directly accepts a float array. However, there is one issue. The method ignores an important parameter, the number of particles to be drawn. Therefore, if your array contains non-initialized elements with 0 coordinates, the draw raw points method also will draw them. Please keep an eye on this red circle. Inside this, you see the red dots. And all of them are disappearing when they are becoming initialized. So we decided to go with a different solution, and I would call it a life hack. We can get an access to a native Android canvas from the Compose canvas with embedded extension. And as you remember, Lottie does the same thing. And in this case, we can completely reuse the same logic without creating any additional methods for working with the Compose. However, this solution has a small drawback. It's not multi-platform, and it looks like Right now, multi-platform is very popular. And unlike the previous approach, where we worked with the Compose canvas with interfaces. And in the future, I hope that the Compose canvas method from the interface will be extended to support the number of particles to be same as the native Android API. And at the end, we repeated some stuff about recompositions. We got the approach how we can avoid excessive recomposition in some cases. And we got some life hacks how we can decrease the memory allocation when we draw on the canvas. So thank you for your time. Draw smartly without recomposition. If you have any question, I'm still working around here on the conference. And here there is a link to the GitHub with the all example from the presentation. Sorry. Yeah, that's end.